Yes, so just briefly a little bit about myself before I go and talk about parallelism and concurrency. So I have a background in academia and then more recently in industry. I founded this Haskell consultancy company along with some colleagues of mine. And so we do, we help companies that use Haskell. That's basically what we do. So we do training, we do development, support, planning. We help people who are thinking of using it or people who are already using it. We support the compiler and tools and all sorts of things to do with Haskell. Okay, parallelism and concurrency then. Or maybe I should really say parallelism is not concurrency. And we'll see what I mean by that. Okay, so what's the point? We want to make programs faster. Right? We always want to make programs. Everyone wants to make programs faster for whatever reason. It might be because you want to deal with more data, or because you want to use less hardware, cheaper, save money, or you might want to get the answer quicker. There's lots of reasons you want to make programs. Everybody wants to make their programs faster. So parallelism is about making programs faster by using more hardware, like CPU cores or GPU cores or whatever, big vectors, whatever. Okay. So, but parallelism is hard, and if you have written or tried to write many parallel programs, you'll know it's hard. Getting real speed-ups and making the program still give you the same correct answer is hard. And there's various reasons for that. We actually have to understand what our programs are doing. We've got to understand our programs better when we try to make them run in parallel. We need to know what they're doing, what they're doing at runtime, not just statically what the code is calculating. We need to know which bits of the program are taking a lot of time. We actually have to start profiling our programs. And then we have, particularly you have got to understand dependencies, data dependencies within the program to be able to know what could be parallelized. And then you have these killer issues like the parallel work granularity versus the overheads. Is it worth spawning off another task to go and do this, or is the overhead of that make it just not worth it? Right? That's something that comes up again and again with trying to get real performance improvements with parallel code. And then you have these horror things, threads and shared variables and locks and non-determinism, and that all makes life difficult. So some of those, I think, are intrinsic. So in particular, parallel work granularity and having to understand our programs. I don't think you can get away from that when you're trying to make them run in parallel. But some of these issues that make it hard depend on the programming model that we choose. And I'll come back to that. So concurrency, on the other hand, is a way of structuring programs. Right? And it's structuring programs to use like multiple threads, or activities that work independently of each other, and then sometimes communicate or synchronize. So for example, threads, shared variables, and locks, it's one model. Or Erlang style, lightweight processes and message passing, that's another concurrency style. And you're typically, when you're dealing with concurrency, you're typically reacting to events from the outside world. And that's really sort of what makes it inherently non-deterministic, is that you're getting events coming in any old, and you have to deal with them. You don't get to choose what happens next. The rest of the world determines what happens next. So you've got to react to things incoming. So it's inherently non-deterministic. And concurrency is also hard. I mean, programming is hard, but concurrency is particularly hard. And so you've got deadlocks and data races. If you're accessing data without taking the lock, you get non-deterministic behavior. You always get non-deterministic behavior. It's inherently part of the concurrency model that there can be non-determinism. You might try and reduce it or eliminate it, but it's there. Testing becomes very difficult with concurrency because there's all these possible interleavings, and on a blue moon you might get a different interleaving than the ones you normally test, and that makes it crash, and that's really, really hard to test. And concurrency makes parallelism even harder. So a lot of those difficulties I mentioned a moment ago to do with parallelism, those are really difficulties to do with concurrency. So in particular, all the problems that you have with shared variables and locks and threads, non-determinism, data locks, data races. These are all things that come from concurrency that we also often have to deal with in parallelism that makes doing that difficult. Right? And one of the most horrible things to do is take a nice sequential program that you understood and then try and parallelize it using concurrency, and suddenly it becomes horrible. It becomes much more complicated, and it's much harder to read, it's harder to maintain, it's harder to test. It makes us unhappy. except it might run faster, right? And that was the reason we did it. But everything else gets worse. Okay, I've been bashing concurrency, but obviously, concurrency has its uses. When you're using concurrency right, it makes your programs better. It makes them easier to understand. If you're writing something which naturally has to deal with events from the outside world, it's very often much nicer to write a threaded program than a big, complicated event machine. So servers are the obvious example of that sort of thing. You've got an interaction with a single client. You can think about that kind of in isolation, and then just have lots of those in threads simultaneously, rather than having to think at once about your interaction with all the clients simultaneously. You can think about one, and concurrency lets you structure your program in that way, which makes it nicer, easier to understand. Okay. So I've said parallelism is about making programs run faster, and concurrency is ways of structuring our programs into these multiple activities. And these are really kind of orthogonal things. They're related, but they're orthogonal ideas. So one is about performance, and the other is about how do we write the program, the structure of the program. So why am I making this song and dance about distinguishing between these two things? Because very often people just sort of use them somewhat synonymously, right? And it's so that we can think about what it is we're actually trying to do, right? If we're trying to make our program run faster by making it run in parallel, then do we really want all those things that come with concurrency? And very often you don't. We'd really rather not if we could avoid it, right? Now, so I'm going to claim, and I'll show you, I think, convince you, that all the combinations of parallelism and concurrency make sense, right? Certainly, no concurrency and no parallelism makes sense, because most programs that we write are not parallel and they're not concurrent. They're ordinary programs. Concurrency with no parallelism is what we've been doing for years with single-core computers and running multiple, operating system processes or multiple threads on a single processor. Right? That makes perfect sense. And then similarly, running multiple threads on multiple CPUs. That also makes sense. So parallelism with concurrency. Those both make sense. So we're going to be concentrating on that. What does it mean to have no concurrency and yet to have parallelism? Now, obviously, my talk is going to be also is how do we all do all this stuff in Haskell? And so Haskell supports both concurrency and parallelism, and it has pretty good support for both. We have a relatively traditional approach to concurrency. We have threads and mutable variables, and threads synchronized by communicating using mutable variables. And then on top of that, you can build other libraries like message passing style, actor libraries, and other higher level things on top, asynchronous, futures, all that sort of nice stuff is all built on a substrate of the basics of locks and mutable variables with locks and threads. But we also offer a bunch of different styles for doing parallel programming, and all of these are parallel programming without any explicit concurrency. And I will spend the rest of the talk explaining what that really means, how that works. So we've got a number of different styles. We've got expression style, data flow style, data parallel style. We have these multiple styles because not every problem fits the same. The problems are different, and some just work better with one style of parallelism, and others work better with others. So it's not. With concurrency, there's fewer models, maybe. With parallelism, there's a bit more variety. So, okay, each of these in Haskell is implemented as a library with some underlying support from the runtime system. And as I say, yeah, these different styles are suitable for different sorts of problems. And I hope it'll, as we go through, become slightly clearer, which styles make sense for which sorts of problems. Now, I can't help but say something about concurrency in Haskell, because we actually have a very nice story about concurrency in Haskell. If you know anything about Haskell, you'll have heard of the I/O monad. Concurrency in Haskell uses the I monad. That means that it's this sort of imperative sub-language of Haskell where we can interact with the outside world, we can send messages, use the network, file I/O, whereas the rest of Haskell is pure functions. But the I/O sort of imperative sub-language lets us do all of traditional imperative programming. We have lightweight threads. That's the critical thing. Very lightweight threads. We have a a slightly nicer story about locks and mutable variables, where we combine the lock with the mutable variable. So you can never accidentally access the mutable variable without taking the lock. So that eliminates some bugs, but fundamentally it's still locked, so you can still get deadlock. Software transactional memory is a thing that we have in Haskell. It was developed partly in Haskell. And this gives us, rather than locks, which are non-compositional, you can get deadlocked by taking locks in the wrong order, and that means programs, you can't compose programs when you've got this issue of locks. With software transactional memory, you can compose transactions, and that's really nice. I'm not going to talk anymore about that, but if you're interested in STM, look it up. It's great stuff. And the other really nice thing is that we have traditional style blocking I/O. Which I think is underappreciated. I'll say more about that in a second. Yes, so Haskell threads are very cheap. Like in Erlang, like Erlang's lightweight processes. You can have tens of thousands of them, and that's no problem whatsoever. Right? These are clearly not using operating system threads, right? These lightweight threads are scheduled across cores by the runtime system. And the blocking for I/O in these lightweight threads works as you would hope, which is that it just blocks the one lightweight thread. If you have a thread in Haskell and it reads from a file or writes to the network and it blocks, that just blocks that one thread, and all the other threads carry on, right? Just as you would hope it to work. And there is a way also to make calls to foreign C code, for example, and have that not block every thread in the runtime system as well. So I think it is true to say that I/O in Haskell is kind of I/O done right? You've probably heard about this events versus threads debate when it comes to how should we do high performance, high concurrency I/O. Events faster or threads nicer, right? We can do both. We can get the performance of event-based I/O. We have these tens of thousands of threads all running on one core, say, or two cores, and it's using epoll underneath, and so we get all this nice event style. The underlying mechanisms in the runtime system really look like what you would get in an event-based server. But the programming model that we have on top is traditional blocking I/O, which is just a much nicer model for writing code. You don't have these, well, if you've ever written any Node.js stuff, it's horrible. The callbacks become really, really complicated. And even in .NET, where you've got these async future things, if you look at most of their examples, mostly what they're doing is actually traditional sequential I/O. They're not taking advantage of any asynchronousness in the sense of running two things at once. They're just, when this file has finished reading, then do the next thing. And when that finishes, then do the next thing. And then when that finishes, then do the next thing. That's just sequential, standard, imperative I/O programming. Why do we have this async stuff? It's just because .NET has heavyweight threads, and so you're forced into doing all these other things. If you have lightweight threads and you do traditional blocking I/O, it's really simple, and it's really nice, and it scales really well, and it runs on lots of cores. Anyway, that's a rant. Because I think people are, especially with Node.js stuff, it just seems so crazy. Okay, parallelism without concurrency, right? That's really what I want to spend most of my time talking about, and that's the sort of maybe slightly mysterious thing if you've not seen it before. So we often call this deterministic parallelism, or pure parallelism, right? And it means that we write a program that's not explicitly concurrent. So this is fundamentally a declarative notion. We're describing what we want, and then we have some way of executing that program in parallel. Okay, now let me give you an example. So SQL queries. SQL is a programming language, in a sense. Okay. So I think you'd agree with me that an SQL query doesn't express any concurrency. It doesn't say, do this, do that, synchronize, pass messages, right? There's none of that. It's just a pure declarative description of what we want the result, what the result should be. And the queries are deterministic, right? Given the state of the database, there's no non-determinism in there. But the database execution engine has the opportunity, if you buy Oracle or something, that it can actually use multiple cores. It can use multiple OS threads running on multiple cores to execute a query. So that gives you, I think, the notion of how you can have a declarative non-concurrent description of a problem, and then an execution engine which itself executes in parallel. And to make the matter slightly confusing, that execution engine may itself be using concurrency to achieve parallelism, but the program you wrote, the SQL query, has no concurrency. So that is parallelism without concurrency. Because concurrency, remember, is not about the execution. Concurrency is about the structure of our program. What are we expressing in the program? Okay? So determinism, deterministic. This is deterministic just in the usual sense of the word, right? That it always gives you the same answer given the same inputs. And this is what most programs are like. Most of the programs we write, most of the time, are deterministic. And that's good, because that makes it much easier to test and reason about. And, ones that are using random number generators, yeah. But most of our programs are basically sequential and deterministic. And so, of course, if it's deterministic, then we get all these lovely properties. It doesn't depend on the number of cores we run it on, it doesn't depend on the scheduler. We'll always get the same answer. It can't depend on the scheduler because we have to get the same answer. So whatever the scheduler does, whatever the OS is doing, we have to get the same answer. There can't be any data races because that would give you non-determinism. And there's no deadlocks. Sounds lovely, right? So how do we do that? So I give you the example of SQL, but how do we do this sort of stuff in a more general, what you would more recognize as a more general programming language? Okay. So one big class of this is parallelism that's available within just pure expressions that you get in a functional language. So this is a really trivial example, but I hope it gets the point. So if we have two computations, call f on x and g on y, and if those are relatively expensive, they take a long time to evaluate, then if we take the sum of fx and gy, then we have an opportunity to run these two things in parallel and then do the addition at the end, right? And I think you'd agree that, like the SQL, this expression does not express any concurrency, but we can evaluate this in parallel if we have a mechanism for doing that. And you can see how that might work, right? So if we have a mechanism, so we can use the parallelism, get the result sooner, so that we've got parallelism without concurrency. So that's the sort of basic idea, and that's what works nicely in a functional language, particularly in a pure functional language. And this idea we can push a very long way. So this is a really, really trivial example, but this idea goes a long way. I mentioned purity. This works particularly nicely in a pure functional programming language like Haskell, because we know that evaluating fx and evaluating gy doesn't have any side effects. So there can't be any interference between, if we evaluate them in this order or that order or in parallel, it doesn't matter, we'll always get the same answer, which isn't always true in a hybrid functional language, which allows imperative side effects as well. Whereas Haskell, you can guarantee this. So it doesn't mean you can't do this in other functional languages, but we get a safety guarantee that you can always do it if you're doing it in a pure functional language like Haskell. So closely related to this idea of parallelism within expressions is parallelism within expressions when you're dealing with big arrays or collections. And this we call data parallelism. So it's all about doing the same operation in bulk on a large number of elements in some collection, typically arrays. And because the idea is that each computation on each element is independent of all the others, then we can do the whole lot in parallel in one go. So the typical examples are things like big vectors, matrices, arrays, and operations in terms of those. And I'll come back and talk a bit about that later, another library we have for doing that. Now, maybe to convince you that this is real, I think I'll tell you a little bit about how it's implemented behind the scenes. Because parallelism is, after all, about performance, right? So we need something that's going to make this work well, not just something that is nice in theory. So behind this beautiful veneer of pure parallelism, we do need something to really evaluate it in parallel and do it well. Right? And so at some level, it has to use operating system threads because that's the only thing the operating system gives us to make use of cores, multiple cores. And the implementation mechanism has to guarantee the deterministic pure property of the high-level language, right? Go back to the database example. If you've got your database evaluation engine, it's using threads and locks, and it's actually quite a hard job, the people writing that, to guarantee that it always gives you the correct answer. That they have all the problems of deadlocks and locks and all the rest of it. So your implementation mechanism has to guarantee these deterministic properties. But you can do that once and then reuse it again and again. And it's obviously vital that the implementation of that is of a high quality so that you get the performance that you're after, and so that it's correct, right? Fortunately for us, we have Simon Marlowe, who's written the GHC runtime system, has been working on that for years and years, and it's a very good quality implementation. So the GHC runtime system, GHC, if you don't know, is the standard Haskell compiler, optimizing native code compiler. So it has a runtime system, it links in with your programs, and that runtime system provides these threads, lightweight concurrency, and that's for the concurrency support. But it does it by using a single operating system thread per core, more or less. There's only one running at once anyway. And these lightweight threads are then scheduled across those multiple cores. So it has a thread scheduler in there, and it's got a garbage collector, which is relatively good. Generational, all that sort of stuff, and interacts reasonably well with running on multiple cores. So, how might we evaluate this in parallel? So, the runtime system has some special support for evaluating individual expressions in parallel with whatever else it's doing at the time. So we can take some unevaluated expression, like f of x here, and we spark it off. And what that means is that expression becomes available for the same core or maybe another core to take that unevaluated expression and evaluate it. And if you do that on another core, then you've achieved some parallelism, right? So we might spark off f of x onto another core and have that evaluated elsewhere, and then on the core that we were running on already, continuing evaluating gy. And there we've achieved some parallelism. So let's talk about this spark notion and how this is implemented. HEC just stands for Haskell execution context, but you can think of it as a core. So each of these things are two. So here we've got two cores. Those squares over there are threads running on those cores. So so core 0 has got two threads running on it, and HEC 1's got nothing running on it at the moment. And then we've got this spark queue. So each core has a queue of these sparks or tasks. And tasks are created by already running threads using this primitive called par, which I'll come back to in a moment. But that takes an expression and says, spark that off. And so what that does is it sticks a new spark into the spark pool, or queue, in fact. Now, the other core, notices, because it's not doing anything, it was idle, there were no threads running on it at the time, it notices that it's not doing anything and says, can I steal a spark from either my own queue, well, that was empty, or I can steal a spark from another core's queue. So it stole that spark from the first core and started a new thread to start evaluating it. It actually only makes a thread the first time. When that thread is done, it will go and look for more sparks. So we only pay the cost of a thread startup once. And also, that's also a lightweight Haskell thread. So this is really very low overhead. Speaking of low overheads, so the spark pool is a lock-free work-stealing queue. That's basically the de jure concurrent data structure for this sort of thing. It's about as fast as you can go. Each spark is just actually a pointer to these expressions, which is in fact just a function pointer. So evaluating is just calling that function, calling through that function pointer. And as I mentioned, that thread only has to get started up the first time. After that, it hangs around and looks for more sparks. So this is actually a very, very low overhead evaluation mechanism. It's about as low as you can imagine going, really, for this sort of thing. It's just pointers and jumping to things. And because of this low overhead, this lets us take advantage of more fine-grained parallelism than we might be able to otherwise. If you're using operating system threads, there's a much higher overheads there in the startup and the switching costs and all that sort of thing. So for that, you have to have much larger chunks of work to be able to profitably take advantage of it, doing it in parallel. Here we can actually take advantage of quite relatively small bits of work. But there's still overhead, it's not free. Yes, granularity is still important. Oops. Okay, so let's go back. So that was implementation. Let's move back to the high-level view, what the programmer sees. So we said it's always safe to evaluate both parts of fx and gy in parallel, but that doesn't actually mean that it's going to be faster. It depends on this parallel granularity issue. If the amount of work done overcomes the overheads, then it's profitable. If it's not, then it isn't. And it's pretty hard to determine that sort of thing automatically. So people initially had this idea, oh, in a functional language, it's all pure. We can just evaluate everything in parallel, and it'll be brilliant. It doesn't really work. Overheads will kill you, because there's a huge amount of very fine-grained parallelism, but you can't really take advantage of that small grain. So fully automatic parallelism, we're not going to get that, really. So you, as the programmer, have to decide what it's worth evaluating in parallel. And in any case, when you start making a program parallel, you've often got to restructure it anyway to expose more parallelism. So this is a programmer-directed thing. We don't get it totally for free. So as I mentioned before, we have this low-level primitive called par, which is a thing that sparks off these sparks. And it has this slightly strange. If you've seen Haskell types, this might look strange to you. If you've never seen Haskell types, don't worry about it. What it does is it says, so it takes two arguments, and it says when the result of this par is required, then we're going to start evaluating the first argument, and then so start evaluating that in parallel. Create that spark, let it go off to another core, and then on this core we'll evaluate the other argument and return it. Okay? It seems like perhaps a slightly odd, but that's the primitive, and all the other things we can express on top of that. So let's do that with this example. And again, this is very low level. This isn't what I would normally write in a real program, but I just want to show you how that low level implementation mechanism connects to what you might do at an expression level. So here we are the programmer annotating what we want to be evaluated in parallel. So this very much makes it uglier, but we'll come to higher level ways of doing this sort of thing in a moment. So using the par primitive, so okay, we have to say we'll bind x prime to the first bit of work, bind y prime to the second bit of work. Crucially, that doesn't evaluate them yet. That just gives them names so that we can talk about them, but it doesn't strictly evaluate them. That's crucial, right? Because it's no good. We have to spark off bits of unevaluated work, right? That's really important. So then we say par off x, so spark that off, and then start evaluating the next bit. Now, psec. It turns out we also need, in addition to be able to saying evaluate this in parallel, we also need to be able to say evaluate this serially, sequentially, here, now, rather than doing it on another core. So we say spark off the evaluation of f of x, and then in this core, here, now, do the evaluation of g of y. And then we'll return the sum, right? And psec is another one of these primitives and has a type that looks the same as par, but all it does is it evaluates the first argument now and then evaluates the second argument and returns that. And that turns out to be important because remember I said both of those are both the x prime and y prime are unevaluated. If we didn't have the psec, there's no ordering on which of these should be evaluated first. So the compiler might decide to start evaluating in this core x prime, and that would be a bad thing because x prime is supposed to be being evaluated in another core. We want to evaluate y prime on this core, so we have to say that. Right, so this is low level, okay? But I think it connects what we're doing in pure expression. So this is all still pure expressions, and it connects that with the underlying implementation mechanism, evaluation mechanism. Okay, so on top of this, we have this notion called strategies, parallel evaluation strategies, which is a library implemented on top of these par and pseq primitives. And a strategy describes how to evaluate something in parallel, and something maybe like big and complex, a complicated data structure, rather than just a single expression. So we have this thing called a strategy type, and the A is the type of a strategy for evaluating things of type A. Okay? And then using is a combinator that says, right, given this value, an unevaluated expression, I'm going to evaluate it using this strategy. And that will give me back the evaluated result of the same type, but it was evaluated in parallel using the strategy which described how to do the parallel evaluation. So there's a bunch of basic strategies for sort of single expressions. No evaluation, evaluate sequentially, or evaluate in parallel. So you can imagine that our par is basically just a thin wrapper around that par up there. But it's as a strategy. And then on top of this, we can build strategies, we can compose strategies and build strategies for working over data structures, for example. So there's one called par list, which is a strategy for evaluating lists. And it takes as an argument a strategy for evaluating the elements. So what it does is it evaluates all of those elements in parallel, and it uses that strategy on each element. So for example, if we had a list of more complicated structures, and there was parallelism available within the elements in the list, then we would say par list applied to our strategy for the element. If our elements are small, we might just be using rsec as the sort of just evaluate it serially. No further parallelism within the elements. Now, granularity. I keep mentioning granularity. It's very common that the data structure we have doesn't naturally map to the sort of chunks of work which we'd like to evaluate in one go, right? We might have a data structure, sometimes you need to split into more independent bits of work. Sometimes you've got many independent bits and you need to coalesce them. You've got maybe too much parallelism available and the overheads would kill you, and you need to coalesce work into bigger chunks of work. And so we can do that, again, in this strategy style by making additional strategy combinators which modify the data structure before, no, I'll just talk about this example. So par list chunk is the idea is that we've got a long list of things we want to evaluate, and we can evaluate them all in parallel, but they're too small to evaluate individually. So what we want to do is say, let's take the first 10 and evaluate those as one block, and then the next 10, and the next 10, et cetera, right? So maybe if we have 10 of them together, that's big enough to be worth doing in parallel, whereas one individually was too small. So we're chunking them up and evaluating those as a single parallel task. So yes, what that's doing is it's increasing the granularity by a factor of whatever integer you plug in there. So let me just give you a very small example from a real program that I wrote for a client last year. This was part of a bigger program that was dealing with portfolios and generating reports based on portfolios. And we have a few hundred portfolios, and things are changing with them all the time. And we want to evaluate these reports and send them off to someone else. And we have lots and lots of them. So we can profitably take advantage of parallelism. And this using par list chunk 10 rseq was the only change I had to make to the entire program to then suddenly make it run on 4 cores perfectly. And that's really nice when that happens. Yes, it scaled perfectly. So this is using that par list chunk I mentioned a second ago. So we're saying reports, which is the unevaluated as yet, reports based on analyzing some portfolios, and that's a list of these things. And then we're going to say evaluate that using this par list chunk strategy. And I determined by a little bit of empirical experiment that chunking them into 10 meant that it was enough to overcome the overheads. When it was 1, then you got some speed up, but it wasn't. The overheads were too high, and 100 or 1,000 was too much because I only had 700 portfolios, but 10 was about right. And there's usually a medium range in the middle that will mean that it'll work reasonably well for 2 to 16 cores, which is the sort of the realistic range at the moment. If you had much bigger SMP machines, you would have to do a bit more tuning, but you just have to change the parameters there. So we can get really good results like that, but parallelism is still hard. Okay, I don't want to give you a false impression that suddenly magically everything is easy, there are still difficulties. And you can see already that I've had to think about the granularity here to get good performance. But once I did, then I did. No, I'm going to skip that bit. I was just showing you can do map reduce and all that. Yeah, I mentioned granularity and this being still difficult. What you really need to solve these issues is good profiling tools. And we've got some reasonably good profiling tools. Because there's quite a few pitfalls that you can run into, particularly to do with this granularity issue. Your work is too big, you get imbalances between, you might have, if you've got 2 cores and you split your work up into 2 things and they're not perfectly the same amount of work on each, then you're wasting 1 core by the time you get to the end. So you want to have smaller sized units of work so that you can balance them between cores better. Or in the worst case, you have fewer bits of work than you have cores. That's clearly too little. Too large, then you get killed by the overheads. And there's a few other details that to do with sparks. The evaluation mechanism. Spark pools might be full, or you might be sparking something which had already been evaluated. There's things that can go wrong. So we need to use a profiler to work out. And we have this profiler. The runtime system does event logging, has this binary event log format, and it's quite low overhead, so it doesn't interfere with the evaluation of your program too much. And then ThreadScope is this graphical tool which looks at these event logs and gives you a visualization of what's going on. So what sort of things can we see with it? So the main screen shows us the overall utilization on all cores. That's the top one. So we can see, that's 4 cores is the top bar up there, and so we can see that, in this section of the program we're using 4 cores mostly, and then after that, we're only using 1 core. And then if we break it down by what's happening on each core, you can see that indeed it's all cores are being used at the beginning, and then something goes wrong because after that it's clear that we're only using 1 core. So that might give us a hint about what was going on. It also shows us the garbage collection. These orange bits are garbage collection. So you can see here we're probably doing a major GC. So we're pausing evaluation and doing GC there. And GC, as in parallel programs, can often be an issue because we typically, when you're doing things in parallel, you often end up with just more data structures in memory. You're retaining more stuff quite often. And garbage collection doesn't scale perfectly, so GC can be an issue sometimes. And we also have in ThreadScope something specific to do with this Spark evaluation mechanism, because there's some particular problems that can occur with that, and we've got some new graphs that help you identify some of those problems. So we have a graph that shows you how many sparks are being created and converted. That means put into the Spark pool and then taken out and actually evaluated. So these red ones here are overflowing. And we also see the size of the Spark pool. So we can see here, this corresponds to the program from the previous slide. So we can see that the Spark pool is full for this bit, and after that it's empty. So that's another symptom of there's no parallelism available. Once the Spark pool is empty, there's nothing to evaluate in parallel anymore, and that's why only 1 core was doing the rest of the work. There was no more parallelism. So then your next step would be, why are there no more sparks after? And it turns out it's because we're overflowing the Spark pool. We're generating 100,000 sparks right at the beginning of the program, and our Spark pool is only 4,000 big or something. And so that's not the right strategy. You have to generate sparks as you go along, and not just generate 100,000 up front. And so those are some of the issues, and you can see what's going on with these sorts of graphs. A particularly nice one that I like to do with granularity, I've not got a picture of it, but we have a histogram of the spark evaluation time. So you can see sort of how many sparks you have that are really tiny and how many sparks you have that are really big. And that can help you to see if you've got lots of ones that are sort of below the threshold of being worth it, or if you've got some that are just so enormous that you maybe are getting imbalance problems. And that's quite handy for that granularity issue. Now, how much time do I have? I may just have to skip REPA, which is sad because it's rather cool. Maybe I'll just tell you briefly about it, but not go into the code. So REPA is a library for this data parallel idea, right? This idea of expressing algorithms in terms of arrays and then getting parallelism semi-automatically, or mostly automatically, by this method. So you write, yes, the idea is that you write your algorithm in terms of bulk operations on arrays, like transform and compute this array based on that array, and these sorts of operations. And you compose those all together to make your algorithm. And then the library automatically takes your array that you're trying to evaluate in parallel, and it splits it up based on how many cores you've actually got, and then runs, one core for each chunk. And so that deals with the granularity issue quite nicely, and basically automatically. With the par stuff I was showing you earlier in the strategies, you have to think about the granularity all the time. With data parallelism, because of the nature of you're expressing, that you have an array, every single element of which could be evaluated in parallel. There's a huge amount of parallelism available, and so the appropriate thing to do is just to automatically, if you've got 2 cores, split the array in half, send 1 half to each core, and have those evaluate those separate parts of the array. And that can be done fully automatically. Once you've described your algorithm, that splitting up and evaluating using a gang of threads can be done automatically. And that's really, really nice. And there's lots of algorithms, particularly kind of scientific and simulation sort of algorithms, which can be expressed quite naturally, quite short programs in this style. And this takes advantage of lots of Haskell cool features, type system things, to make this all work nicely, which I'm afraid I don't have time to go into. No, but let me just show you this demo, because it's very cool. This is Ben Lippermeyer showing off REPA. So he's doing some video processing, live video processing. He's got on his MacBook 8 core, well, it's 4 cores hyper-threaded, I think, so it's 8 apparent cores. And he's got this canny edge detection algorithm. So it's an image processing algorithm. So each frame that's coming in from the video camera, you don't have long to process it, obviously, and you're writing, the edge detection algorithm is specified in terms of like a function. The function at each pixel, it's a function of the other pixels nearby it in the original frame, right? And so you can play with the thresholds and da-di-da-di-da. But just the nice thing, the code is quite small. The code is quite easy to understand. It's quite similar to the sort of mathematical specification of the thing. So you have this nice short code. You never have to say how it's split up. It just gets done automatically. And as you can see, it runs really nicely across lots of cores. And so when that works, that's really cool. Okay, I can't tell you about the types of the stuff, but that's another time. Except the key idea is that we have this distinction between describing the array that we want to compute as the final result, and then compute it in parallel. And there's this, it's called a delayed array that describes the thing we want to compute, a sort of declarative style, and then separately, now we'll evaluate that thing in parallel. That's the key idea that it's resting on. Okay. So, I've talked about a few different styles. So expression style I focused on. I very briefly talked about data parallel style, this array business. And also, yes, concurrency. You can also write parallel programs in Haskell using concurrency. And that's okay. And these are all pretty mature things now. The parallel runtime system has been being worked on since multi-core started getting hot, and every release it's been getting better and better. So the scaling now is really pretty good. There's a couple others worth mentioning. Data flow style parallelism. If you've come across that before, it's all to do with like fork join style. And we can do that, again, in a pure way, which is really interesting. Nested data parallelism is like the array parallelism I was talking about, but instead of just having dense arrays, dense multi-dimensional arrays, matrices and whatnot, we can have arrays that can contain arrays, which is not the same thing as multi-dimensional arrays, right? Arrays that maybe contain arrays. And that allows you to do things like sparse arrays, sparse matrices, because you can represent a sparse matrix as matrices, sparse matrices as arrays that can contain descriptors of pointers into indexes, other parts. And so you can represent those things. And then the clever part of it is that the compiler automatically flattens out all those arrays into one great big array and then does the same old thing of chunking it up and sending it off to different cores. So that massively increases the expressiveness of this array style. So it extends it into, sparse is one example, but there's many other examples of nested data parallelism allowing you to express things in this array parallel style. And finally, GPU programming. And the GPU programming is actually very much like REPA, this array parallel programming style, but with the extra complexity of having to say whether this array lives in GPU memory or lives in CPU memory. So there's an extra type that says whether it's in the GPU memory or the CPU memory and makes sure that you don't accidentally, or that you're explicit about when things move back and forth. But it's very similar style in that it's all this array business. You're writing bulk operations on arrays, and then we generate on the fly GPU code and send it off to it goes via the CUDA compiler and sends off to the GPU. But the programming style is very much like this array, like the REPA stuff. Also, just want to mention that that this is mature technology that you can go and use. Simon PJ he was speaking in the keynote this morning, wasn't he? I was still finishing my slides. So we were working with him to do this 2-year project to show that the parallel Haskell really does work, that it is mature technology now. So what his idea was to get a bunch of commercial industrial users and say, we will support you to write the parallel code that you want to write. So that he hired us basically as consultants to help those groups. So we had people from Los Alamos laboratories, a small fisheries company in New Zealand that looks at models of fisheries for the New Zealand government, and it does lots and lots of simulations, and these simulations take a long time. And if they could do that quicker, they'd be able to do more iterations of their modeling, and that would be a benefit to them. And a few other groups. In particular, one guy who is working on highly concurrent web servers for ISP in Japan. And most of these groups were not existing Haskell experts, so we had to do a little bit of they knew Haskell a bit. They were beginners, basically. And so we had to do so part of what we were doing was teaching and then pointing them to the right techniques and tools. But basically, there weren't really any significant problems. Yes, the people had to spend a little time learning Haskell, but they got that relatively quickly. I was quite impressed. Because functional programming is often a big leap for people, and particularly pure functional programming. But they did pretty well. We had to develop a few missing libraries that they needed. The Los Alamos group needed a high-performance parallel random number generator that was statistically good enough to use in Monte Carlo or some sort of simulations. I don't even know if it was. I don't understand the physics of it. And we extended these parallel profiling tools, the thread scope I showed you earlier. We added the Spark profiling into that. But basically, they did okay. So in particular, the Los Alamos guys, so they were writing this physics simulation, high-energy particle physics, something to do with black holes and astrophysics. And they had an existing, mature, single-threaded C version of their simulation, which they'd tuned, and it was fast. And we never got the Haskell version to be as fast as the C version. We got it to be about half the speed, which was we were happy with that. They still thought they could do better, and maybe they can. But that was on one core, and the Haskell version. Well, the Haskell version was much nicer code to start with, and it scaled really nicely. It was quite easy to add parallelism to it, and it scaled very nicely up to the number of cores that they had available. And actually, an interesting thing. This isn't really so much a parallelism thing, but just programming in a nice language is nicer thing, is that eventually the reference implementation became the Haskell one, because after working with that one for a while, they realized that it was much clearer and nicer and easier, and it was much easier to tell that it was giving the right answers. I mean, it's hard sometimes in simulations to tell if it's giving you the right answer, because it's hard to specify in some of these simulations what the right answer should be. So eventually, the C version was adjusted to match the new reference implementation, which was the Haskell one. And they also wrote, I've been talking about SMP concurrency here, but on this project we also did some distributed concurrency. We wrote this Cloud Haskell thing, which if you ever hear Simon talking about, is rather fun. And they also wrote some versions using MPI in Haskell. MPI in Haskell is still MPI, it's still ugly, but the cloud Haskell one's not too bad. And I think maybe the best result is that the programmers who are actually doing it were much happier with it. They were happy with having a parallel version. You know, it was a parallel version that wasn't painful. You know? So I think that's a good result. And the performance was good, right? The performance, they were beating the C version because they were using multiple cores, right? So they got good performance, the code was nice, everybody was happy. So that's it. Thank you very much. Questions?
Is it like that the par words would only work because it's lazily evaluated?
Yes, that par thing does rely on the lazy evaluation, yes. I imagine you could come up with similar things that would work in an ego language. But you'd have to do things, instead of being a single expression, it would have to be like a function applied to an argument, for example. Yeah, so you'd say par of f and x, rather than just saying par of f applied to x. That would be the distinction, yeah.
Talk about you have to overcome the overhead cost of split setting.
Yeah, granularity, yeah.
Is there any tools or benchmarks that you can run? You know, I've got this machine, I've got this code that I want to parallelize. Is there anything you can run and say, well, your overhead's going to be somewhere around this microsecond, so you need to think about different iterations before you do that? Or is it just you use some of those profiling tools and adjust them?
Yeah, I haven't actually done that yet. What I really want to do is on that histogram of Spark evaluation times, put like a red line in there to say anything below this line is like below your threshold of overhead, and it's like, you know, this is now, you're spending half the time on the overhead now, it's not worth it. I haven't done that experiment, but it wouldn't be that hard to do, right? It's just a benchmark you could write. And yeah, you're right, it'll vary from one machine to another, of course. Although it'll be broadly similar, because it's all the same. You know, it'll be, you know, it's like cache and that sort of thing. Yeah, it's a good idea. Yeah. Any other questions? Or? Yeah.
But has anyone tried, like, instead of having to explicitly put these keywords and these strategies and basically sort of has anyone just tried describing the type of data you're going to get to category and just getting the system to try parallelizing bits and then try not parallelizing them or doing it and then just comparing the strategies, trying to automatically generate a parallelizing strategy based on the distribution of data?
Okay, so the question is, has anyone tried sort of more automatically working out what the right parallel evaluation strategy is? So I think the nearest thing that people have tried is they did an experiment where they took a whole bunch of programs that had not been written for parallelism, and they said, how much parallelism is there really available in this? Let's pretend that we could evaluate everything with no overhead to doing things in parallel. How much parallelism is really available? And they found that in most programs it was only about 2 or 3. And that was very fine-grained parallelism as well. So you might be able to apply the same. So I guess the way you might go about that would be to write a strategy which followed the full structure of the data. So, you know, a list of this, of that, of that, right? So you'd write the general strategy which looked at everything and do some logging while you're doing that, and then analyze that later and go, oh, okay, you know, we're going to have to cut it off here, and oh, it's even worse than that. We're going to have to chunk the. It's a good idea. I don't think anyone has really tried doing it, because you can do it as your programmer yourself, because you can change because you're writing the strategy separately from the algorithm a lot of the time, right? That was maybe the thing I didn't really make clear. I had to skip a bit. Is that very often you can separate these things. So changing the strategy can then become just a matter of fiddling with it, recompiling, run your benchmark. Okay, no, it's still overheads. You know, let's chunk it here or increase the factor there. So it's not that hard to do once you've got into that. Once you started attacking it, optimizing your strategy is not too bad. But yeah, you possibly could do it more automatically. You have a question?
Yeah. Can you extend these tools like REPAL, R function, to run on many servers, not only many clouds, in distributed environment?
That's a research problem. Okay, so the question was, can you extend this idea of data parallel, you know, computations of arrays that we've got working in an SMP multi-core setting? Can we extend that to doing it, you know, in the cloud? And the answer is that there's people who really, really want to do that, and there's a company I know that's working on that, but I think that's quite a tricky problem. In principle, it seems like it's totally possible, but I think there's some tricky engineering challenges. That'd be really cool. I'd love to see that. Because I've been working on this Cloud Haskell thing, and I've been working with the people who've been working on REPA, and it'd be lovely to combine the two, yeah. Because the model, in principle, works for that. And Simon P.J., if you listen to him, says that data parallelism is really the only way that we're going to have really large-scale parallelism, dealing with thousands of cores, maybe on one machine or across hundreds of machines. The strategy stuff, you can scale up to maybe 16, 64, I don't know how many cores, but there'll be some limit to that. It's not going to scale into the hundreds of thousands. But data parallelism, that really could. If you've got a lot of data, there's no principal reason why that shouldn't scale really well. Because they're really independent. You're really just splitting it off and evaluating that section in separately on each node. I think we better wind it up.
Thanks, Duncan.
Not much.
Thank you.
Thank you.